So our first speaker is Zaman Yazbeck, who is working at École Centrale Lyon, and she'll be talking about identification of solid oxide electrolyzer parameters. So the floor is yours.
Okay, good morning and thank you for being here. I am Zaman Yazbeck, a PhD student in my second year. So today I represent a part of my work related to parameter estimation of solid oxide electrolyzer. It's a part of my work in my thesis, which focus mainly on the fault detection and prognosis using model-based approach. So it's important for me to have a calibrated model and reliable parameter estimates at the beginning of life of the system. I'm working in a company named Genvia in Grenoble, and it's in collaboration. My thesis is in collaboration with CEA in Grenoble and Laboratoire Ampere in Lyon. So the outlines of my presentation will include an introduction about the solid oxide cells technology in general. Then we will go to see the structure of the mathematical model without so many details, but just to have an idea about the input, the output, and the states with the parameter vector to be estimated. And then the problem or the objective, which is the parameter estimation problem, and how we solve it, which methodology that we use to solve this problem, and the validation of it using experimental data with the results and the analysis, and finally a conclusion with the perspectives. So nowadays, you know that we are facing a climate change and global warming problem, and we have a lot of ecological issues. So these have a social, economic, and health consequences. So it's important to develop and commercialize alternative technologies and work on green energies. Like hydrogen, for instance, which appears as an interesting vector and can be produced using different ways like the electrolysis of the water, using electricity and steam and water. And solid oxide cells are one of the most promising technology to produce hydrogen, and it can work in the reverse mode. So it means that we can, using hydrogen, produce electricity. Electrolyzer in general, is an electrochemical converter that transforms electrical into chemical energy. So the electrolyzer cell, it consists on two electrodes, a cathode and anode. So the water, which can be in liquid or gas phase, is fed to the cathode side, where it will be used to produce hydrogen and oxygen ions. These ions are diffused to the anode side and to be oxidized to produce oxygen. So solid oxide cells, specifically, they work on at a very high operating temperatures between 700 and 800 degrees and atmospheric pressure. And this is to reduce the need of the chemical energy and to have a faster kinetic in terms of reaction. And so it means that to have like high efficiency. So many cells are put in series together to produce more hydrogen, and this is what we call a stack. And this stack is put in a hot box or in a furnace. And this will put a limitation on sensors placement, and thus we will have just few measurements. So
just a question. When you say few, I mean, you mean you don't have many sensors, but for each sensor you've got a huge amount of data sets or not?
Can you repeat?
You mean few measurements, but
few sensors.
Few sensors.
Yeah.
Okay. But
few access.
For each sensor, you can have.
Yeah, of course. Yeah. So to model this system, there's many models that we can see or take from the literature, but it depends on the purpose of the model, for what are we using the model, and what level of details we need from this model. So for us, we used a 0D model where we didn't take a spatial distribution of the current, the temperature, the flow rates inside the cell, and so on, because we need this model to run in real-time simulation and to be used for fault detection and prognosis purposes. So, as an input vector, we have the flow rate of the steam, the current, the air, the inlet temperature of the gases, and the temperature of the furnace. As it states, so we have the partial pressures of the gases, the hydrogen, the steam, the oxygen in the cells, and this is calculated using mass balance equations. And the thermal model is presented by the TR out, which here we consider it as the average presentative temperature of the stack using energy balance equations. As a measured output, we have the voltage of the stack and the outlet temperature of the air. To model the voltage, we use Butler-Volmer, Ohmic law, and dusty gas model for the diffusion equation. So for as other electrochemical models, there's many parameters that need to be estimated. And here in our case, we have 10 parameters. We can split it into electrochemical parameters and thermal parameters. So the goal is to build a systematic approach to have to estimate these parameters, but the model, of course, is nonlinear, especially the voltage, and we have large number of parameters and just few measurements. So to solve this problem, the tool that we use is to combine sensitivity analysis with the sensitivity assessment of the effect of the parameters on the output, combined with the gradient-based optimization that we use, which is Gauss-Newton. And this is to prioritize the highly sensitive parameters and to have like a more reliable estimation of the parameters. Please. So here we consider that the identifiability of the parameter is based on the sensitivity of the output with respect to the parameters. Before introducing the methodology, let us define some sensitivity variables, which are Sx and Syt, the sensitivity matrix of the state and the output with respect to the parameter vector lambda. So if we take our state space equation and we do the first order partial derivative of these equations with respect to the parameters around the set of nominal parameters from the literature and from the characteristics of the system, we will get the sensitivity differential equations in the next slide. Yeah. So we can calculate, express the output sensitivity matrix in function of the state sensitivity matrix. And here, so we extended the number of ODEs to have the number nx plus the number of the ODEs from the sensitivity of the state. So to calculate the Jacobians here of the ODEs of F and H, we use the symbolic toolbox, which is called Casati, because it's a bit challenging to do the derivation by hand, especially for the voltage, which is a fast symbolic tool based on which is based on automatic differentiation. And then after, if we take a specific input profile, we calculate at each time step the sensitivity Syt by integrating Sx and the states. So in the end, if we concatenate all these sensitivities in a big matrix Sy, where each row is the sensitivity of the output at each time step, and we transpose this matrix and we multiply it by itself, it will give us the correlation matrix. And then based on this, using Gram-Schmidt to reveal or to show the linear dependence between the parameters and to sort the so we use Gram-Schmidt to sort the magnitudes of the sensitivity of the parameters and to have the linear dependence between the parameters. So what is done in literature is so what is done in literature is to choose an initial guess at the beginning of the parameters, then do the model integration with the sensitivity calculation, as I said before, to propagate the states along the input trajectory that we have, and the sensitivity matrices. Then we do the sensitivity analysis where we build our big matrix SY by concatenating all the sensitivity of the outputs in a big matrix and calculating the correlation matrix, and then calculate using Gram-Schmidt. We show the magnitudes of each sensitivity of each parameter. Then we do a parameter grouping based on these calculated magnitudes. And then we do a sequential parameter estimation depending on the groups. So it means that we start by the group 1, which has the highest sensitivity, and we fix all the other parameters to their nominal values or to their initial conditions. And then we go to the group which has less sensitivity while keeping all the other parameters fixed, and so on until all the parameters to be estimated. But what we did, what we changed is that, what we changed is that instead of using a fixed linear dependence between the parameters, because it's a nonlinear model, we include this in the optimization problem, in the gradient-based optimization problem. We will see later, because it's the linear dependence between the parameters is not fixed. So this isn't taken into account later in the gradient-based optimization. We'll see how. So we define our cost function, which is the mean square error between the simulated output and the experimental one. Then if you do the partial derivative of the cost function J, we see that the output, the output sensitivity matrix SY appears. And based on Gauss-Newton iteration, we can see that the SY, the big SY matrix appears here. So this is the Gauss-Newton iteration, and we have in it the sensitivity of the output with respect to the parameter. So for the step beta here, we use an adaptive beta based on line search algorithm to be updated in each iteration. And for SY, what we did is that to normalize it and to truncate it. We'll see why. So for the normalization, first we multiplied by a matrix gamma, which is a diagonal matrix where the elements are a fraction between the order of magnitude of lambda over the order of magnitude of the output. And then, because we have different parameters with different order of magnitude, and then after normalizing it, we truncate it using SBD decomposition and to keep always the highest sensitive parameters. And so it means that we are updating, we are like directing the algorithm to update the parameters and to search in the most sensitive direction. Yeah. So we use this methodology and we validated in using experimental data. And we use for the input profile, we use a time window at the beginning of life of the system, because the operating condition of the system is quasi-static, but at the beginning of life of the system, they do something called performance mapping, and this is just to check the behavior of the system and to compare it with the manufacturer, with the catalog of the manufacturer. So we use this time window where we have a dynamic operating conditions and have ID curves. We are varying the current with different current ramps and at different flow rates. We applied the methodology first using a fixed beta for the step of the Gauss-Newton iteration, and with line search technique also, where we update beta in each iteration. So here we want to say that it's important to use an adaptive beta, and this is to keep the monotonicity of the cost function and to avoid the divergence of the algorithm. And maybe for the convergence of the algorithm. So for adaptive beta, after 150 iterations, more or less, we converge to 1.3, and for fixed beta, it takes more iterations to converge. And on the left, we can see the cross-validation of the model using a different data set. So for beta, we said that we used a line search technique, and we put a maximum limit to it to equal to 200. And high values of beta means or decrease the cost function rapidly, whereas less or smaller steps will result on a slower validation or decrease of the cost function. So for the estimates, we start by an initial condition based on literature and the characteristics of the system based on the geometries. And then we try fixed Gauss-Newton method, but the algorithm break after a few iterations. And we can see here, especially there's like the values that we got after the algorithm breaks are very far from the initial guess. And this is because why the algorithm break? This is because we have some negative values, for example, for the RS or the gamma anode and gamma cathode inside the logarithmic function. And this will lead also to ill-conditioned sensitivity matrix also. And we tried with the MATLAB function fmin_con, but with just the positivity constraints. The cost function decrease, and we have like a good, I mean, in the end, we have a small cost function, a small error between the simulation and the experimental data, but we don't have like a physical meaning of the parameters, especially for the activation energy. And the anode is the order amplitude is -3, while it should be 2. And the convectivity coefficients are too big. So we tried with fixed beta and adaptive beta. So we said that what is specific of the algorithm that we implemented is the normalization of the sensitivity matrix and the truncation, because it does not update all the parameters in each time step, in each iteration. I mean. So here we can see the rank of the truncated sensitivity matrix. And just to remind you that we have 10 parameters at the beginning to estimate, but you can see here that it does not update all the parameters. So it means that also the linear dependence between the parameters is varying in each iteration. And the algorithm adapts the parameters that has like a significant singular value. So we are projecting the error on the most sensitive directions. So after estimating the parameters, we calculated the confidence interval to see and to check how much we can trust these parameters, because this will be used for the prognosis later, and where many parameters will vary slowly in time. So this is just to see which parameters we can update or we can trust. So the assumption is to consider that we have a normal distribution of lambda, and since the standard deviation is not known, so we calculate the confidence interval using the t-distribution. So this is the confidence. So this is the margin that the lambda can change, vary between it, and t is the upper critical value of the t-distribution, n is the number of observation or the samples, and the standard parameter error, sigma, is calculated using the square root of the inverse, the diagonal of the inverse of the correlation matrix. When we calculated this, so we calculated this, and here we show in this column the relative or the normalized version of the confidence interval, and we can see here that some of confidence some of the normalized confidence intervals are very small and some of them are very big. So they like the big ones are like in yellow. And this means that, so the large confidence intervals means that parameters are not well estimated, and this is because we have low sensitivity of these parameters and low effect of these parameters on the output. And this can be explained that the input profile that we use does not contain sufficient information to have more information about these parameters. And high sensitivities means that will lead to narrower confidence interval, and you will have more reliable parameters. So to conclude, I presented what we did for the parameter estimation, and that what we used for the estimation of the parameters in the model, the solid oxide electrolyzer. And it's an extension of Gauss-Newton method, where the parameters were the most sensitive directions are automatically updated in each iteration instead of clustering them into groups like what they do in the literature. And we validated this methodology using experimental data, and we compared it with the classical Gauss-Newton, the Pham one with just the positivity constraints of the parameters, and we calculated the interval estimation, the confidence interval based on T distribution. So for the future work, we are working now on validation, or to validate or to check this approach using simulation and using the model in a case where we know the parameters, and to study the effect of the noise. And also later to design an optimal experimental data to estimate all the parameters and the other parameters that have like a big confidence interval. And this is all to use it later for the prognosis part and to update the parameters that are varying slowly in time because of the degradation of the system. And thank you for listening.
We have some questions. Yes, Guillaume.
Thank you for the talk. It was very interesting. So my first question is, I may have missed something, but so you have to select singular values.
Yeah, in the end, yeah.
And how do you select the threshold
Yeah.
between what you assume that is small and
Yeah.
what is big? Because I don't see the impact during your, or you don't talk about this.
Yeah, I didn't indicate this. Yeah. Can I send you another, like an appendix?
I don't know if you really need the
yes. No, but yeah, it's just we take a relative and absolute tolerance. So the absolute tolerance. So the relative tolerance is when we take the first singular value, which is the highest one, and we multiply it by like a value that we choose randomly, like 10 minus 4 and so on. And we choose another, the absolute tolerance, and to keep, if the singular values are low, to keep always the highest singular values. So yeah. So in the end, it's in function of the first singular value in each iteration.
And my second question is linked to, so it was a bit fast for me. On your results, when you have an initial value and you estimate the parameters, have you noticed that from time to time you keep the initial value and you never re-estimate this value? Because,
I mean, during the iteration?
Yeah.
It happens. Yeah, okay. It happens. Especially for some parameters related to activation energies.
And what is the impact of the misspecification of these specific initial values? So you test, you know quite well the initial value, you say, okay, I trust that. I run my simulation, so it doesn't change. Only for this specific parameter. If you misspecify this initial value, what is the impact of the result?
You mean if I choose different initial conditions?
Yes, for this specific one. do you see an impact on the other results? That's
on the other parameters, you mean? I'm not sure, but I think yes, because we have linear dependence between them. But I didn't try this in simulation, but it's also in the work that we need to do in the future. But I think yes, because there's a linear dependence between them.
And I've got a last question on the perspective. So you're talking about effect of noise.
Yeah.
So if I'm correct, you just assume that you've got output noise. So you just have a noise on the or even on your model, but you don't assume that you may have a misspecification or a mistake on the equation of x dot. So you don't add process noise in your case.
No. No, but here when I said the noise, it means that it will be like if I have noise, so I have the big error. So this will be translated later in the singular values. This will give a big singular value, and the inverse of it will lead to like a singularity in the or like a low rank of the sensitivity matrix SY.
Okay.
Thank you, Zaman, for a very interesting presentation. Well, now I have all the tools, so I can go where I want to go. First, well, let's go here. So when you do that, in fact, speaking about noise, continuing on the Guillaume's question, when you suppose this expression, in fact, SY transpose SY is the covariance matrix of your, well, information matrix of your identification problem. When you suppose that your output data are perturbed by white noise, only white noise. But anyway, so
it's just an assumption.
Yeah, but you could verify on the residual if it's really white also. So
the validation.
Yeah, so on validation and even on your identification data, you could look at the residual, so y minus y sim, and look if it's white. And if it's not white, then you could whiten it with a noise model, like we did in the spring school. So if you remember.
You can prove it.
And anyway, so that's interesting, and it's also but of course, if there is process noise, then well, basically, everything becomes much more complex. But you can start with this. That would be a good idea. So if it was interesting because in fact you are developing a method allowing to get a good estimation of some parameters when you have non-informative data. Because if you were there with FPIN-Con, you say, well, we got very small residuals, but with other parameters. So in fact, you have a lot of parameters which can explain your data. So what you do, you fix some parameters to the nominal value, and you only update the one where you. And then, of course, the question of Guillaume is very interesting. So what's the consequence of having a wrong first estimate on those parameters? But that you can do in your perspective. The first bullet will help you to do that. And of course, well, the last point is of course very interesting. It's to, well, if you have non-informative data, you can always ask yourself, how can I make this the data more informative? And in fact, you have all the tools, because I guess with your information matrix, you just have to make that information matrix well, strictly positive definite, so larger than something.
So usually what they do in literature here, from what I read, is that they use Fisher information matrix.
But that's that.
Yeah, exactly.
And you maximize the determinant of it, and that would be a solution. And so you would just change U for that. So, and well, that's also interesting to know if it's possible, given your given your number of outputs and your number of inputs, that you can really make it strictly positive definite. Is it possible?
I think
Even
because here for the input vector, the only thing that we can use for the excitation is just changing the current density.
yeah, but that's what that's came to
Instead
my.
of changing, because there's a lot.
Because here you have a lot of inputs, so but you can manipulate all these inputs, but no, it looks like there is yeah.
But so I think because, for example, what they do in electrochemistry, the people who are specialized in this, usually when they want to have more information about this, they do something called impedance measurement. So they do like a current excitation at different frequencies to have more information from the voltage about the internal resistance of the system. So I think for us, we can just like play or control the current to make.
And the others, they are given.
The others, because the others, so for example, for end of air is, so with electrolysis of water, we are producing air. But here we have an input airflow rate for thermal purposes. So this can be, I think we cannot use, especially, and the same thing for the major temperatures, yes, because we have thermal temperature, thermal parameters. I don't know.
Yeah, but so you have more
operating conditions than inputs. So, the temperatures, for example.
Yeah, but no, we are controlling the temperature of the furnace.
Okay. But the air temperature, for example, is the ambient air.
It's like an operating condition. Yeah.
So
No, it's not. It's also controlled because it should be like the steam and the air should be heated before introducing into the stack. So it's controlled, but it's fixed. I mean, so they preheat these gases, but they control the temperature of the furnace. But it's not at ambient temperature.
Yeah, but as you said, these inputs, for example, for the temperature are more open conditions because it's not dynamically changing. You're not making them varying, and you'll be estimating your impedance or your model of the system around an operating conditions.
Yeah,
so for me, it's not really a control input. It's the conditions of the system. So it's more the operating conditions.
But you could then optimize on this condition also,
Yeah.
if possible. Yeah, but they are constant, let's say. So,
Exactly.
Yeah.
Yeah, I'm not sure because here we have the thermal parameters that are very dependent on the, like if we don't have a dynamical profile of the temperature, these parameters will not be, we don't have any information from the experimental data about these parameters. So I'm not sure, I don't know.
Okay, and so what are the, sorry, do you have another question?
No, go ahead.
So I was wondering about your inputs that are changed. So you showed us about the current, but is there another input that you are changing over time, that is changing, that you're really controlling?
Yeah, the temperature, so the temperature of the oven is varying. I didn't show it, but it's varying with the input in the input profile that I use.
No, what I mean is more when you're doing system identification.
Yeah.
The control inputs are the inputs that you are directly injecting on your system.
Okay.
Which are the ones that are really dynamical where you have it really injected on your system?
So it's the current and the steam flow rate. Adjust this and the temperature of the furnace.
Okay. And so can you show us the input the current that you showed us?
I can't if you want. You just stop with this one?
Yeah.
Yeah, here the temperature.
So how did you design this input?
I didn't. I took it from the experimental data that they have. So
Okay.
at the beginning, they do something called ID curves. So they increase the current and they decrease it to show how the voltage is, like what is the behavior of the system as in terms of voltage.
Okay. So I was more about, I was a bit concerned about in system identification, you have a certain number of parameters to estimate. Okay, and it depends on what you have injected in the input.
Yeah.
So, in order to well estimate your parameters, it means that your input should be persistently exciting.
Yeah.
So, do you try to see if your input is sufficiently rich in frequency, in the spectrum of the input, so that you will be able to estimate, because you have something like 10 parameters to estimate.
Yeah.
So, it means that you need at least 5 rays on the spectrum of the input to be able to well estimate your parameters.
If it's linear.
She's assuming that she's working on a working point.
No, I didn't try with the frequency domain, but this, I don't know, maybe can be done for the with the future work.
Yeah.
Yeah, I think it's important.
Yeah,
because he would just.
You wouldn't have the experiment.
So
You would be limited in the validation of the model.
no, but if you are able to do to get some.
No, it's not easy actually to have like a lot of experimental data and design what I want, because they have like in the CA they have like standard protocols to apply. So I'm limited in the experimental data that I'm using. So that's what.
But it's just to check that
Yeah,
input is sufficiently rich. It will help you in the estimation. Yeah. And yeah, it's
yeah, thank you again for the presentation. And it's not quite in there, you get confidence intervals for all the parameters or just for an identifiable subset?
No, for all the parameters.
So for some of them,
So for
be
some
very, very large.
Yeah, so when it's very large, it means that this parameters is not well identified.
And have you tried perhaps some simulated data to check whether your confidence intervals are calibrated? I mean, if you repeat identification with different data sets, do the confidence interval correspond to true uncertainty? Because there are many assumptions going on there, reciprocity, wideness, that the optimization has gone well. That would be
yeah. But you mean to validate it in simulation using simulated data?
Well, frequentist uncertainty means that if you repeat the experiment with different data sets from a family, then the uncertainty represents the range of the estimated parameters. Then you also have Bayesian uncertainty, which is slightly different. Either one or the other can be.
And you may also use the bootstrap approach if you're not really.
Yeah, even in bootstrap. Yeah, that's the real.
So I guess what Marco says is you make simulation data where you know everything.
Yeah.
You apply your method. You compute your uncertainty, your confidence intervals, and then you validate them by doing 1,000 experiments with other noise.
Yeah.
And then you look at the identified parameter vector, and you look at the uncertainty given by you make 10,000 estimates, and you look at the uncertainty there and you compare. Yes, that's what you got the
And then on real data, you can check whether your uncertainty is calibrated on the output. I mean, whether you are 95% of the time, if your error bars are well calibrated, it means if you have the uncertainty that you project to the output, it really contains your data with a given probability.
But I guess what Guillaume said, if you have a bad first guess of the non-identifiable parameter or non-informative where you don't have information, there that bias will propagate to all the other parameters. But that's the only thing you can do. That's not a criticism about your method. Given the data, it may be the best thing you can do. Trust your prior. But if your prior is not good, well, then the bias will propagate. So effectively, then the need of real informative data is really there. So then that's otherwise, you cannot do much.
Thank you.